held up well during the hurricane break. And so I pushed back, of course, the due date for the first homework assignment, which consisted of 2 sections. I pushed that back to today, for it to be due at 2:00 p.m. For those of you in class, physical copies perfectly fine. Online people, upload it the way you did the upload assignment. And if you want to do virtual, but you also want to turn in the homework physically, you can slide it under my desk, or not my desk. Let me try it again. Slide it under my office door. If you're, if you are on campus early and then you go home and then you don't feel like coming back to campus for this afternoon class, you can just slide it under my office door. If you want to do it that way, just shoot me an email. Hey, where's your office at again? Or you just find it. It's on the 3rd floor of this building. So you can do that as well. It's not like you have to show up here to turn it in physically, but just letting you know the options. And so, yeah, I'll grade those. So normally what I do with homework, I'll pick just a random subset of problems that I'll grade for correctness, maybe like 4 or 5, that offers a good representation of the concepts I want you to know. I'll grade those, each problem out of 5 points, and then the other ones they'll be for participation. So it's really no way of you knowing which ones I will grade for correctness or not, but that's generally the way I do it. So yeah, I'll grade those and have those hopefully done later this week. It shouldn't take too long. You all think, was it fairly straightforward, a little tricky, or? Okay, yeah, that was mostly geometry stuff. So let's go ahead and, so we're gonna go ahead and pick up where we left off, which was, and again, I'm going off of the notes that I posted to Moodle at the beginning of the semester. We were talking about trigonometric functions, and we talked about how, we talked about the trig functions themselves and equated them either using this x, y, and r notation, or using opposite, adjacent, and hypotenuse, which is more of a visual aid when we have a triangle for which opposite, adjacent, so any sort of spatial thing can be applied to. So if we have a triangle ultimately, and we use x, y, and r if we don't have a triangle. So pretty much we used sort of both of these in tandem for the first 2 examples. So we went through those 2 already. Example 3, I got cut short by the end of class. So I'm just going to go ahead and start example 3 over, just so we can all warm up to this idea. So in examples 1 and 2, they gave us a point, and we were able to plot the point, draw a triangle, and then figure out the trig values that way. Here, you may notice in example 3, there is no point. They give us a line instead, and some condition. You might think, well, how is that helpful? The way this is helpful is because on that line, we can find a point, and then it ends up being the same problem as examples 1 or 2. So this says all we need to do is find a point such that x is less than or equal to 0. Now the problem with just picking any point arbitrarily, which is what we talked about last time, I'll write this in red because I'm going to end up erasing this. If we were to end up picking x is equal to 0, then if you were to plug that into this line equation over here, we would get that y is equal to 0. So the point that we would inevitably get would be 0, 0, which is not good because in our definition, xy had to be a point other than the origin. The origin is the point 0, 0. So we cannot pick that. So I'm going to erase all that, and we'll go ahead and instead pick x is equal to 1, or negative 1 rather. Just the next point that's less than or equal to 0. So if we pick that, then let's solve for y. So we're going off of this equation over here. I'm plugging in negative 1 for x. And we can find out pretty quickly that y is equal to positive 3. So in other words, the point now is negative 1 comma 3. I have my notes written just in case to make sure I don't screw up anywhere. All right, so we find this point, negative 1 comma 3. So it's treated the same way as we did in example 1 or 2. So now we can plot that point. In fact, I'll give a lot of space here. Say negative 1's here, and then 1, 2, 3. Just to give this a lot of space so I can draw. So this is what we have found. This point being, of course, negative 1 comma 3. We went to the left 1 and up 3. And so, as I was mentioning last time, there's this idea of triangulation, which I will visualize in red, which is where you take that point and you drop straight down to form a right triangle. So if I say the word triangulation, that is what I'm referring to. And there's a reason why. It's because right triangles give us some really simplistic properties that we can utilize. So what we ended up doing, so this whole time, this line that we drew represents the terminal side for this angle, which is called theta. So that line helps us form the angle, but the triangle helps us form a visual aid. So now we just turn our attention to the triangle itself. So the triangle itself has, well, it has dimensionality. It has an x value or width, it has a height, and it has a hypotenuse value, or the slanted line. So we went to the left, negative 1 times. We went up, positive 3 times. And to figure out the value of the slanted line, the hypotenuse, we have to use the Pythagorean theorem, which I wrote at the beginning. And we did a few of those before. So this was r is equal to square root of negative 1 squared plus 3 squared. So that looks like the square root of 10. So that is the value of the hypotenuse. They use r for radius, but it's the same idea. It's the hypotenuse. So square root of 10. So it's kind of messy, but our main goal was to construct that triangle. That triangle is the most important thing here right now. So the beauty of triangulation is we can take that angle and visualize it instead as just the triangle that we have constructed. And using that information, now we can go ahead and figure out the 6 trig function values. So I'll go ahead and start off with the first 3. So sine as we mentioned up above, was, and this is when you can use SOHCAHTOA if that helps you, if that mnemonic memorization technique helps you, or remember that it's opposite over hypotenuse. The angle for which these spatial relative values are referencing is this red arc that I drew. So what's opposite of that? Looks like it's 3. It's 3 over the square root of 10. 3 is opposite, square root of 10 is the hypotenuse. Cosine is adjacent over hypotenuse. So what's adjacent to that arc? It's -1. And then finally, tangent is opposite over adjacent, which that's just really equal to -3. That one's pretty easy. Now, if you're familiar with trig at all, or if you recall this from college algebra, they refer to something of rationalizing the denominator. In this class, I do not ask for you to rationalize the denominator. That just means, so some nitpicky people out there do not like square roots in the denominator. There's a method you can do to, well, rewrite it. This isn't my math lab though, so I frankly do not care. You can leave it just like this. I grade everything, so this is perfectly fine to me. It's one just annoying algebraic step that you don't have to worry about. So these answers, so sine and cosine, the denominator is not rationalized, but you can keep that. Anyways, so those are the first 3, but we still have 3 others. We have cosecant of theta. Cosecant of theta, the reason why I write it straight across from sine is because they are reciprocal identities of one another. Cosecant is just take the value of sine and flip it. That's it, just flip it. Sine's 3 over the square root of 10, now it's square root of 10 over 3. Just like that. Secant, the reason why I write it across from cosine, same idea. Really, it's just negative square root of 10 because the 1 doesn't matter. And finally, cotangent, just -1 over 3. I know it said find cosecant and secant, but I figured I might as well just write them all down. So that would be the 6 corresponding trig values. Does anyone have any questions about that process? Is that pretty straightforward? Okay. Google Meet people. Okay, cool. All right, let's move on. So really, example 4 says repeat example 3, but pick a different point. Because remember, the whole problem started off with picking some arbitrary point. So, and that whole process snowballed from when we picked x is equal to -1. So what happens if we pick another x value, just randomly? Do we get a different set of answers for our trig functions? Let's find out. So it's the same example as before, but we cannot pick the same point as we did last time. So that means we cannot pick x is equal to -1. Naturally, the next x value is x equals -2. So x is equal to -2. And then if we plug that in, as we did before, so it's the exact same problem. It's just we're picking a different x value. So then y is equal to 6. Which means the new point we have is negative 2 comma 6. From here, I'll put more emphasis on the left-hand side because we are going to the left 2 and up 6. We triangulate the same way. To force that right triangle, and then we know 2 of the 3 dimensions of the triangle already. So negative 2 for this one, 6 for this one. We went to the left 2 and up 6. Going to the left is a negative direction and going up is a positive direction. Naturally, we can go ahead and determine the radius or the hypotenuse in this case. This is using the Pythagorean theorem. Negative 2 squared plus 6 squared. If I remember correctly, that's going to be the square root of 40, which doesn't really simplify too nicely, just like square root of 10. So you don't have to simplify radicals in this class either. That sounds annoying too. You don't have to do that here. You can if you want, because you could simplify that, but not a big deal. So you find the radius is the square root of 40. So we can go ahead and fill that into our triangle. So that is the hypotenuse value. And then here I'm just going to do, I'll just do cosecant and secant. So remember, the triangle helps us, it's a visual aid that helps us break down this representation, but instead use the triangle to figure out all the spatial values. So it gives us a visual aid, like I mentioned. So now we have a concept of opposite, adjacent, and hypotenuse. So cosecant, well, that's 1 over sine. And sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. And then that is just square root of 40 divided by whatever the opposite was, which is 6. Secant, that's 1 over cosine. Cosine is adjacent over hypotenuse, so now we use hypotenuse over adjacent. So, well, up to here, is everyone okay with that? Is that pretty straightforward? So, Google Meets. Okay. So, that all seemed a little bit redundant, but it highlights a bigger idea of, well, does the trig value change? And it might seem interesting that here, cosecant here is square root of 40 over 6. Cosecant up here is square root of 10 over 3. They look different. Are they different? They are the same value. They're the same exact value. So it turns out that this is equal to the square root of 10 over 3. If you threw it in the calculator and got a decimal approximation, you could see that. You don't have to. or if you rationalize the denominator, you would see that. But I just, the most important thing is the concept. It's the concept of seeing that, and you might notice it in the note at the very bottom that kind of ruins it. The values of the trig functions do not depend on the point chosen. You can choose any point you want, whatever is most convenient for you. So whatever point you choose on the line, it will serve the same exact purpose. You will get the same value. So if you do that on your homework, you all may choose a different point, but I'll probably take out my calculator and just test your approximations with the right answer if you pick something crazy. But that is the idea. So with that being said, let's go ahead and move on to something very important, quadrantal angles, which I already talked about quadrantal angles before. Quadrantal angles, if you recall from the last time, the last class lecture, it's any angle that lies on any one of the axes. So if I draw an XY plane, then 90 degrees, that would be a quadrantal angle. Or if you kept going to this axis, that would be 180 degrees. And I think you might see where I'm going with this. If you go down to the negative y-axis, that would be 270 degrees. And then the whole way would be 360 degrees. So any angle, so they go in multiples of 90. So a number, you could think about it as a number is quadrantal if it's divisible by 90. That's another way you can look at it. But they go in multiples of 90. That's what I'm trying to emphasize here. So anything, and these are very important for, we'll see this in example 5, why these are so special, why we give them a special name. So scroll down a little bit. So it's pretty much asking us to do the same exact thing as before. Really, it gives us less information, but there's a reason why. So example 5 is very similar to example 4 and example 3. So here it says, all right, we're going to draw a 90-degree angle because that's the angle that they're testing us with. A 90-degree angle. And I could have used the box as well. This is a right angle, so I could have used the box as well. So that's 90 degrees. So in examples 3 and 4, what we normally did was we used that idea of triangulation to make a triangle. The problem here is since the angle lies on an axis, we cannot triangulate because basically what they're doing is, in other words, if we have a point on the terminal side, like we had in the previous problems, what we did then was we dropped that point straight down to the x-axis and we formed a triangle. Can't do that with quadrantal angles. That's why they're different. We cannot, so in other words, you cannot triangulate with quadrantal angles. That's a reason why we differentiate them from regular angles. It's because if you find a point on the terminal side, you cannot just drop it straight down and form a right triangle. which means you have to use the formulas. And when I say formulas, if I scroll up right fast, the formulas I'm referring to are those, the x's, the y's, and the r's. There's no concept of opposite, hypotenuse, and adjacent because there's no visualization regarding a triangle. So we have to use x, y, and r. So that's why it's important to know both definitions here. So we scroll back down. So now the question is, all right, we need to find an x, a y, and an r. Well, I don't even see an x. I don't see a y. We're not given a point anywhere. Well, remember that black point that I just filled in right here? Well, right down here. I drew a little point. Because it's on the positive y-axis, and we just proved that we can choose any point on that line, well, we can, like I said, we could choose any point on that line. What would be a point? Blake, what would be a point on that line? You got anything?
0, 1.
Yeah, 0, 1. Exactly. That's it. So we could pick any point we want. 0, 1 would be a point on that line. You could have picked 0, 2, 0, 3, 0, 50. Wouldn't recommend picking 50 or anything. But we picked 0, 1. And now that we have a point, we now have an idea of an x and a y, which is great because our formulas had x's and y's in it. But it also had one more thing, an r. We need to get r. Well, shoot, how do we get r? I don't even see a hypotenuse here. Well, we use the Pythagorean theorem because we have an x and a y. To figure out r, it's the square root of x squared, which is 0, so kind of dull, plus 1 squared. And from here, you simply get 1. So it's not very exciting, but the radius is 1. Or it's hard to say hypotenuse because we don't have a triangle, but the value of r is 1. So now we have x, we have y, we have r. We can use the formulas perfectly now. So sine of 90 degrees, that one was y divided by r. If you scroll up, you would see that. Y is 1, r is 1. Well, guess what? It's just 1. Cosine of 90 degrees is x over r. X is 0, r is 1, and that's just 0. Tangent of 90 degrees, that's y over x, which is going to be 1 divided by 0. Kind of interesting. Thought you couldn't divide by 0. Well, you can't. It's undefined. Let's see. Let me clean this up a little bit. Let's see, we said sine of 90 degrees was 1. We said cosine of 90 degrees was 0. And now tangent of 90 degrees is 1 over 0, so it's undefined. That's it. It doesn't have a value. Tan of 90 degrees is just undefined. It does not have a value. All right, what about the reciprocal values? Cosecant of 90 degrees. Well, We know what sine is. Sine is just 1. So what happens when you flip 1? You just get 1. 1, I'm going to say 1 a lot in this next sentence. 1 is 1 over 1, which is 1. That felt horrible to say. It's just 1, though. Or you can use the formula from above. Cosecant is r divided by y, and you would run into the answer the same way. What about secant? So yeah, secant is, well, 1 over cosine. So you flip cosine, but cosine's 0. So if you flip 0, so what do you get when you flip 0? You get undefined, because you would then get 1 over 0. You would get 1 over 0, which is bad. So then you get undefined again. Now the interesting one, cotangent of 90 degrees. Oops. What is cotangent of 90 degrees? So you might think, all right, cotangent is the reciprocal of tangent. If tangent's undefined, then you might think, well, what's the reciprocal of undefined? It means you can't really use that reciprocal thing because there's nothing to reciprocate. There's no fraction. You might think, well, let me use 1 over 0. Well, I mean, yeah, you're right. From the formulaic sense, this is x divided by y. That is a common problem that students will miss. What is cotan of 90 degrees? Out of context, with no other trig functions around, a lot of students get that one wrong. But this follows the formula. In fact, once we get to how to put these in your calculator, if you put in cotan of 90 using the way that is shown in class, the calculator lies to you. And because it doesn't interpret it, it'll interpret, let me try that again. The calculator interprets cotangent as 1 divided by tangent. I'll get to it when we talk about that stuff. In any case, for the 90 degrees, does anyone have any questions? I mean, we're about to do the same thing for 180 degrees.
Is that the same for like 270? Like 270 degrees, all the stuff for 90?
The only difference for 270 is that the point that we pick would be 0, -1. I'm kind of looking in this general area. I don't know who asked the question. Okay, yeah. For 270, the only difference would be the choice in the point. It would be 0, -1. And then you would just get some negative values in certain places. That's it. So y would be -1, and then, so the only difference would be some negative signs in a few places. So let's move on to 180 here. So 180, like I mentioned, is a quadrantal, which means you cannot triangulate with it. So if you were to draw out an XY plane and graph a 180-degree angle, you would attempt to find a point on the terminal side. And generally, if this was not a quadrantal angle, you would drop from that point to the x-axis to form a right triangle. But there's no height. There's no ability to form a right triangle because we're missing the dimension of height. So we would not be able to have a triangle with any height. So instead, we have to pick a random point on that terminal side. So, Blake, you want to pick another point?
Just do -2, 0. Or, yeah, -2, 0.
Okay, I don't like that. I'm gonna use -1, 0.
-1.
Yeah. It keeps the numbers as simplistic as possible.
I'll remember that. Just use 1.
There you go. Yeah, I try to pick the most simplistic points. And at the end of the day, it all simplifies itself anyways, but let's see. So I pick -1, 0, -1, because we're going to the left for you all. And so we can use this. We have an X and a Y. We could figure out R pretty quickly. We just get 1. Not very exciting, but we do get 1. And from there, we follow those formulas exactly the same once more. Sine of 180 degrees, that's Y divided by R. She would end up getting 0. Cosine of 180 degrees, it's X divided by R, which would be -1. Tangent of 180 degrees, it's Y divided by X, which is 0. 0 divided by -1. Cosecant, you could think about it as sine flipped. So what would cosecant of 180 degrees be? Yeah, that would be undefined. Because if you think about it formulaically as well, it would be R divided by Y. What's Y? Y is 0. So naturally, dividing by 0, it's not good. All right, secant. You can either use the formula or you could just flip cosine. The reciprocal of -1, just -1. Cotangent, it's undefined. So that would be the 6 corresponding trigonometric values. Now, what about, well, later on as we progress, actually before I progress, does anyone have any questions? Well, for which one? You mentioned your calculator says 0 for yeah. Do these all look all right? Did anyone double check me on this? Sure, -1, 0, undefined, -1, undefined. All right, cool. So let's go ahead and move on to. Let's go ahead and move on to example 6, which basically says, hey, can you do this in the calculator? Well, it's a perfect time to grab your calculator. If you don't know how to do this already, make sure that it's in degree mode. And by doing that, by simply typing in sine of 90 degrees, you should be able to get 1. These are values we already found. This is a way to confirm that your calculator is in the right mode. Because some people's calculators, you might have fooled around with it. This happened in the summer when someone took the first test and their calculator was in radian mode for the whole test. I don't know how, but it was. So that's why I want to confirm that everyone's calculator is in degree mode. And you can test that very quickly by confirming that sine of 90 degrees is 1. And then similarly, I mean, all of these values, sine, cosine, and tangent of 90 degrees, we found all of those in the previous example. Cosine of 90 degrees, you should get 0. Tangent of 90 degrees, it'll complain, as it should. So by doing that, your calculator is in the correct mode. Don't change it to radians. Have the course worked out to where we do not touch radians until, I believe, after the midterm. So there's no reason you should go to radians. Unless you want, to make it a little bit more complicated. So hopefully you can all do that in the calculator. And it says do the same for 180. I mean, you could see the values right there. So I trust you can all put it in the calculator correctly. If not, just ask me after class or just shoot me an email. So we are not talking yet about the reciprocal identities. So you might be wondering, hey, I don't know, I see secant and cosecant and cotangent. But when I look at my calculator, I do not see secant, cosecant, and cotangent. And that's because I explain how to do that in a future section. You might already know how to do it. If so, cool. But there's going to be no necessity for it. There is a homework problem that asks you to find secant. It involves secant of 90 degrees and then plus cotangent of 0 degrees. But it wants you to solve the problem by, using the formulas. So that means you need to show your work for that. Just to make sure I know how you do it right. And then after we get all this out of the way, you can use the calculator all you want. So that's how you put it in the calculator. And let's go ahead and move on. And as you would imagine, only use the calculator when the directions say use the calculator. There's some problems where you're tempted to just throw it in the calculator or produce an answer, but you don't show work. So naturally I have to deduct a point or two and just say, hey, show work. So if the problem says use your calculator, by all means, like example 7. So it's a nice segue. Example 7 says use the calculator to find cosine squared of 33 degrees and tangent cubed of 33 degrees. And really example 7 is just a way of determining how to interpreting that notation. So this simply says cosine squared of 33 degrees is the same thing as cosine of 33 degrees. All of that squared. So that's it. And if you do that correctly, and you can put the parentheses as much as I have them here, it'll work out just fine. If you do all of that correctly, and you're in degree mode, 4 decimal places, 0.7034. And I'll do tangent as well, which is the same exact idea, except slightly different situation. It's just tangent of 33 degrees, and then you just raise that to the 3rd power. .2739. Is anyone not getting these values? Well, if you're not getting those values, just ask me at another point. Otherwise, let's go ahead and move on to the next section on using the definitions of the trigonometric functions. So we're going to learn some characteristics about these trig functions. For the homework of 1.3, so for this homework, just since we just finished up this section, I was thinking about having this one and the following section due Friday, and you can turn it in. Well, actually, we don't meet on Friday. Yeah, that's going to be kind of lousy. Some of you like turning it in person. Thursday might not be enough time because that's next class period. Maybe try to get this in Thursday, this section, and if that's kind of a hassle, then I'll push it back to Tuesday.
Just 1.3 or 1.3 and 1.4?
See, I wanted to combine 1.3 and 1.4 together. If I do it that way, I'll just have both of them due Tuesday. Does that sound fine? Okay, cool. Then, all right, so just to clarify, 1.3 and then 1.4 are both going to be due Tuesday, so you get a week. Now, it may seem kind of alarming for the next section that the homework questions, they just, oh my goodness, there's so many of them. A lot of these are just, you'll see that a lot of them are just yes, no, or they're not as bad as you think. The quantity is reflective upon the fact that some of these are just not really engaging. They're like one-line answers. Some of them might be a little bit more engaged, but don't let the quantity of problems, mislead you. So the reciprocal identities, for the reciprocal identities, we've already talked about this before. It just means that sine and cosecant are reciprocals of one another if you have one value. So if you have sine, you just flip it and you get cosecant. If you have cosecant, you simply flip it and you have sine. That's it. On your part, so for the midterm, I don't think I provided any formulas. Actually, I'm trying to remember if I did give formulas for the midterm. Because for the first assessment, it's not an in-class test, which means naturally I cannot hover over you and tell you not to use your notes. So it's open season there. I cannot remember if I gave formulas. The point is, I'm trying to remember if you need to memorize these reciprocal identities or not. It's better to know them really quickly. So do not confuse do not confuse sine and secant. They are not reciprocal identities, even though they both start with S. Do not confuse cosecant and cosine because they both start with C. That commonly happens. It's reverse. Sine and cosecant. Cosine and secant. So, and I recall a student asking, I think on the first day, about tutoring. Yes, so I didn't forget about that. The only tutoring that I am able to notice that's going on in the university is for the Center for Student Excellence. And if you or anybody else shoots me an email, or a few of you shoot me an email to remind me, because verbally I cannot remember anything. Got to shoot me an email. And so I'll send out the link to it, but it's the Center for Student Excellence. They have appointments that you can schedule or you can walk in, I'm pretty sure. But if you're familiar with Tinsley Hall, they completely redid Tinsley Hall, so they could have the nice Center for Student Excellence tutoring center. It looks really nice. Because when I was a student, Tinsley Hall was a disgusting. Never mind. Very moldy. Very
How many
gross.
chapters do you combine per exam usually?
Chapters. So let's say 2. So first 2 chapters for the first assessment, and then I think I append. Well, for the midterm, it'll be the first 3 chapters. And then it's 2 and 2, I think.
To end. So two, like for the exam 3 and then final would be the last 2.
Yeah, so exam 3 is not cumulative, but the final is cumulative. So let's see. So speaking on reciprocal identities, as I was saying, if you know, say, cosecant, then you can figure out sine by simply flipping cosecant. That's it. I mean, that's 2 of your homework problems right there. See, that was just one line. So as I mentioned, they're not, don't let the quantity fool you. It's, some of them are just kind of boring. See, that's it. It's basically asking, can you remember these associations? Something that maybe, in fact, not even maybe, something that will be very important is the determining the signs of the trig functions. So when I say signs, I mean, can we determine absolutely if, say, sine of a value will be positive or negative, or cosine, or tangent, or cotangent, all the rest of them? And the answer is yes. I provide this diagram here, and the way that you would interpret it. So I listed what the quadrants are. Quadrants 1, 2, 3, and 4. They go in a whatever direction that is, a counterclockwise direction. And it tells you if your terminal side ends up, so let's say you're drawing an angle somewhere. Let's say the angle goes all the way, stop it here. So let's say we drew that. Then we could say definitively that tangent is going to be a positive value, which implies that sine and cosine will be negative values. And since tangent and cotangent are reciprocals, if tangent's positive, then cotangent has to be positive. So this tells us definitively that if we know where an angle lands, which quadrant, then we know what the sign of the output will be. And a general memorization technique, all students take calculus. As I mentioned down here, one may use the mnemonic all students take calculus, which characterizes the order of the quadrants for which each trigonometric function is positive. And then I explain all means everything's positive. S in students means that sine is positive only. And then tangent's positive, and then cosine's positive. So that's what that refers to. I'll explain this in the upcoming examples, but you can use the placement of the terminal side of the angle, so terminal side being this side, to determine what the signs of all the trig values will be, negative or positive. And that's actually really helpful information. So let's move on to example 2, which will kind of put this to the test. Determine the signs of the trig functions, and they say for a measure of negative 200. It's not saying determine the trig values, it's saying just figure out if it's positive or negative for each trig function. So where is negative 200? How do we figure out which quadrant that's in? Well, it's negative, which means we have to go clockwise. So this would be negative 90, which isn't large enough. This would be negative 180, still not large enough. So how many degrees do we have to go? We already went negative 180. We got to get to negative 200. So we got negative 20 degrees left. So that would be about right here. And so by determining where this angle lies, so it lies in quadrant 2, which is where sine is positive. So quadrant 2, what that means is sine of theta is positive only sine. So that means cosine would be negative and tangent would be negative. But what about the other three? What about cosecant, secant, and cotangent? Well, the idea of reciprocal association, that implies that the signs will just carry over to their reciprocal counterpart. If sine is positive, then its reciprocal cosecant will be positive. If cosine's negative, then secant will be negative. And cotangent, same with tangent. So there's really two parts of this problem. One is getting to determine how to draw angles in the appropriate quadrant. So knowing how far to go with your arc until you hit negative 200, which really I just go by multiples of 90. And then the remainder, if I don't have 90 left, then I know it's going to run out somewhere in between. And then knowing how to interpret the signs of the trig functions. So does anyone have any questions about this? So we're going to do something fairly similar. It's kind of looking at it from another direction. This will be a few homework questions alone. So example 3, identify the quadrant or possible quadrants where all this stuff happens. So we're almost in essence working backwards. They tell us a condition or give us some conditions, and they want us to determine where an angle must lie. In which quadrant would the angle lie for this to be possible? So for part 1 here, tangent. For tangent to be positive, well, let's look up at our chart here. First quadrant, everything's positive. So tangent could be positive there. Second quadrant, sine. So tangent would be negative. Tangent would be out. So quadrant 1, good. Quadrant 2, not good. Quadrant 3 specifically says tan can be positive. So good. And then the last one, cosine only. So not tangent. So to answer the question, tan will be positive in quadrant 1, which is all, and quadrant 3, which is the T part, the take. So all students take calculus, it's the T part. And that's it. That's your answer, just quadrant 1 and quadrant 3. Question 2, part 2. When is sine positive and when is secant negative? Okay, so let's start off with sine being positive. Which quadrants is sine positive? So everything's positive in quadrant 1. So we'll look at just sine alone for now. Quadrant 1, everything's positive. And what's another quadrant where sine is positive? It's 2, because all students, and what does the S stand for? It stands for sine. So take at calculus, T for tangent, so not sine, C for cosine, still not sine. So quadrant 2. So 1 and 2, but that's just for the sine part. What about secant? Because the table doesn't really address secant explicitly, the table, I keep calling it a table, this thing with all the quadrants and stuff. It addresses sine, cosine, and tangent, and then the reciprocals help us figure out the rest.
So basically, when is cosine going to be less than 0?
Yeah, this is the same thing as asking for when cosine is less than 0. It's just a tricky step they try to throw in the middle of things. And so we play the same game. When is cosine less than 0? So everything's positive. That doesn't sound very negative. Students, that's where sine is positive, which means cosine is negative. Take, so that's tangent is positive and cosine would be negative. And calculus, so cosine, which would be positive, and we want negative. So for sine, we have quadrants 1 and 2. For cosine, we have quadrants 2 and 3. Put it all together, and you see, has to be quadrant 2. That's the overlap. So the answer would be quadrant 2. Because that is the overlap between the two. If sine is positive, or if we're in quadrant 1, then there's no way cosine can be negative simultaneously. So that'll be like 2 or 3 homework questions right there. Does anyone have any questions on that? See, if I could get done with this section, I would be very happy. Okay, so another thing, ranges of trig functions. So we talked about the signs of the outputs, whether they can be positive or negative, but what kind of values are these outputs? What are the size of these outputs? Is there any way to restrict them or know what these look like? And something I think is good to illustrate this is by, if you take your calculator and you just type in sine of, and you just type in any random values, you will start to notice a pattern, I think fairly quickly. And if you type in any value, it will work the same. I'm just typing in various values for sine. So sine of, like right now I have sine of negative 70,547. And then you just type in random other numbers. The pattern you might notice, all of the outputs are small numbers. They're very small. How small are they? Well, we can quantify it. The outputs for sine and cosine will always be in between -1 and 1. Or they could also equal -1 and 1. So remember, that's interval notation from college algebra. That means that the range, all the outputs of sine and cosine will always be either bigger than -1 or equal to, and less than or equal to +1. Tangent and cotangent, their outputs can be anything. So there's no way we can contain that. And then secant and cosecant pretty much says, well, we can be any number, just not one of those really small decimals. So basically sine and cosine switch out with secant and cosecant. So in other words, the values for secant and cosecant cannot be less than 1 or greater than -1. So let's look at example 4. You'll have a question or two about whether this is possible or not. So sine of theta is equal to 2.5. Can that ever happen? The answer is no, it's not possible. The reason why is because sine cannot have a value that escapes that interval. It cannot have a value greater than 1. So for question 2, I think question 2 is fairly interesting because secant is not isolated. Because you might see secant in 1.3 and think, okay, that's fine because secant can be greater than 1. But we have like terms. So this is the same thing as secant of, and that's actually omega, or fancy W for Greek. So combining the like terms, you would get secant of omega is 0.3. And then you ask yourself, can that happen? The answer is no, because the range, well, it has to be either less than -1 or greater than 1, according to this condition up here. So this is not possible either. So that'll be a few questions on your homework right there. Is that okay? I'm confusing about that. Okay, so they define quotient identities and the Pythagorean identities in this section, but we don't really use them yet. They are here, and I'm going to show them to you. We're not really going to do any homework problems that utilize these, and when we do, I will re-emphasize these formulas, but if you do follow along in the book, you're going to see these. We just don't have any need for them right now. We will soon, just not right now. So they're there just kind of for formality's sake. And example 5, I just thought that was a cool problem, but it's not really, since a hurricane had to come through and screw up my timeline. You can just ignore example 5. I was going to prove it using a unit circle and a projection. Don't worry about it. It was just a cool way to prove that a formula works. At least I think it's cool. We'll move on to example 6. And so for example 6, find a solution for this. It may seem a little bit, different than what we're used to. And probably the reason why is because we haven't really had equations with multiple trig functions in them, really. We haven't really had any of that. So these types of problems require you to put your head on the desk. You got less than 10 minutes, hang in there. So it requires you to have the same trig function on both sides, so then you can do some really neat manipulation right afterwards. And so what I mean by that is, so for this problem in example 6, it would be really cool if we can get tangent on both sides. That'd be really neat. Or if we can get cotangent on both sides, or either or. Well, it just so happens that 1 over cotangent, in fact, I've seen that before, 1 over cotangent. I've seen this before, 1 over cotangent, 1 over cotangent. One over cotangent is just tangent from that reciprocal identity. We're going to manipulate that directly. So this is the same exact problem as tan of 3 theta minus 4 is equal to tangent of 5 theta minus 8. So all we did was we took this right-hand side, we wrote it with a tangent. And cool, now we have a tangent on both sides. The homework question pertaining to this one's a little bit more challenging. It does require an intermediate step, so that'll be a challenge problem for that homework. So from here, since we have tangent on both sides, and we're only looking for one solution, we are allowed in this moment to do something that's kind of frowned upon in general, but we can do it here. Let's cancel out the tangents. It's not good in general, but if we're looking for one solution, we can do this. And by doing that, we just have an algebra problem. So we just get that. So that's finding a solution, which means if you plug in 2 for theta, you will end up getting that both sides of this thing are in fact equal. So pretty much an algebra problem. So finally, I'm going to go ahead and use this last amount of time to find all the trigonometric function values for some angle. And they give us a good plethora of information. So what I'm going to utilize first is that theta is in quadrant 2. So why is that helpful? It's because we can draw an angle in quadrant 2. So which one's quadrant 2? It's this one. That's why it's good to know what the quadrants are. So it just says there's some angle in quadrant 2 somewhere. We don't even know what the angle is. It doesn't matter. It's just some angle in quadrant 2. I think we can all agree that that's some angle in quadrant 2. Naturally, we can triangulate because this is not quadrantal. And force a right triangle. So now we have this triangle that we can visualize instead. So off to the side, we instead would rather look at the right triangle that we just formed and try to fill it in. So all we know now is that cotangent is equal to -3/4. So cotangent is equal to -3/4. How does that help us fill in the triangle?
That's adjacent over opposite.
It's adjacent over opposite.
So the
Yeah.
bottom side's gonna be 3, and then the long side's gonna be 4.
So where does
Not the hypotenuse.
so let's start off with the fact that this is let's see. This is in fact adjacent over opposite. Okay, then that means if anything, I'm going to ignore the negative sign for now. I'll put a 3 down here for adjacent and a 4 right here for opposite. That negative sign doesn't just disappear. Where does the negative sign go?
The 3.
It goes on the 3. Because if you notice our triangle that we had, we go to the left. So we go to the left, which is a negative direction. So that's a negative, going up is positive. So having all of that, we can go ahead and figure out the hypotenuse. And if you are good with geometry, you probably notice this is a 3, 4, 5 triangle. If not, this is the square root of 25, and the square root of 25 actually simplifies the 5. 25 is a perfect square. So now that we filled that in, we can go ahead and figure out all the trig functions. And I will be incredibly caught up. So sine is opposite over hypotenuse, which is 4 over 5. Cosine is, of course, adjacent over hypotenuse. Tangent, well, we already know what cotangent is, so we could figure out tangent either way. We already knew cotangent. Secant's really easy to figure out because we know cosine. And then cosecant is 5 over 4. This is a very important problem. We're going to be using stuff like this similarly throughout the whole semester. But alas, I am out of time. I did finish this section on 1.4, so I would like the homework to be Tuesday for both of these sections, 1.3 and 1.4. If we work ahead, maybe I could, well, I'll think about what I was about to say. I'm going to take that back. Try to have that done Tuesday. If there's too much difficulty with it, we can talk about, how to do some of the problems or something. Other than that, in-class people, do you have any questions? Go nap. You all have a good day. Get out of here. Online people, if you don't have any questions, you can go. So I'll stick around.
I got lost at secant of W or omega.
Okay.
Plus one is, I don't understand what secant of W represents. That's the only thing.